Hi, everyone. I'm going to talk a little bit about CE 321, Introduction to Transportation Engineering, and within that, Engineering Economics, which is a very important topic for your FE exam, Fundamentals of Engineering exam. A lot of questions there from this topic area. Very important to understand for decision-making, very critical. And first of all, what I'm going to talk about is that, obviously we're going to talk about some numbers, some numerical examples that are obviously going to be helpful for your FE exam. But I'm also going to discuss where does all this fit in within the planning process, because that's what we're talking about in this module for CE 321 is the broader planning process. And within that planning process, where does engineering economics fit in is going to be some part of the conversation as well. And as usual, we're going to be discussing the slides, and then I'll have also the textbook open here as well. So this is your chapter of the textbook that we're going to talk about. This is chapter 5 of your Fricker and Whitford textbook. So let's go get started right away here. So let's think about the planning process. So SR 361 example, what does that mean? As you know, all chapters in your textbook start with some kind of a real world scenario where the discussion that is being had in the chapter is going to be useful. So in this chapter, or chapter 5, the example is about SR 361, which is an arterial corridor in the city, in the county. In the scenario 4 for chapter 4, Mythica County Commission was asked to study the perceived congestion. So I'm going to go ahead and spotlight this. The Mythica County Planning Commission, MCPC, which is the Metropolitan Planning Organization, MPO, for their location, and was asked to study the perceived congestion on SR 361. As MCPC staff, the Planning Commission staff collected the data and began to apply the 4-step travel demand model, which we're going to learn in chapter 4. Several citizen groups were proposing solution to the congestion. Now, this is where this chapter is important, because we're talking about planning and evaluation for decision making. And obviously, there is a numerical component to the decision making, the benefit cost analysis that we're going to learn to conduct in this chapter. But then there is also this idea of different groups, what we call different stakeholders. For example, they define several citizen groups were proposing solution. And all of those have a different sort of, viewpoint around how they want to have those solutions advocated for, what type of solutions they want to advocate for. For example, the developers, they advocate the reallocation of SR 361 to an alignment that bypasses the city entirely. Okay, so they want the high-speed traffic to sort of go away, so they can do more development here. And then downtown merchants urge the state DOT expand the 2-lane SR 361 to 4 lanes in the city. So ostensibly making it 2-lane road into a 4-lane road will bring in more traffic, might be good for the downtown merchants, at least potentially. The environmental interests want increased transit service, right? So the environmental interests have an interest in not having as many cars using the roadway. So they want more transit service. And then taxpayer watchdog groups and neighborhood want a do-nothing approach. So basically just let it be and don't increase road capacity, because increasing road capacity only encourages more driving, and expensive transit technology is never justified. So this is sort of an idea about different stakeholders proposing different solutions. So for this class, again, because this is just an introductory class in transportation engineering, we're not actually going to try to balance all of these interests. We are just going to sort of focus a little bit more on the numerical analysis side of things. But if you're interested in this stuff, we do offer a CE 528 class, which is the Transportation Economics and Analysis class, where we talk about how do we balance out interest of different groups, how do we think about those questions. And some of those questions are not necessarily engineering related. They're very much political decisions that have to be made. So we have to keep that in mind. So this is sort of the broader context in which solutions get proposed and implemented, is that different interest groups will have different objectives. and they will try to push for those objectives. For this class, again, because this is an introductory class and our goal is to sort of give you more sort of technical nuts and bolts types of tools. So we are just going to look at the economic analysis to determine if a proposed project's benefits justify its cost. We're looking at the economic analysis to select the best alternatives. So those are sort of what we are going to focus on. And then you could think about a little bit more about, multiple criteria. So we'll have some minor discussions. So our goal here would be to sort of focus on the second and the third learning objectives a little bit more. And then I already briefly talked about number one, right? So just different stakeholders being involved. And then how do we rank different alternatives? We'll talk a little bit about that in the end as well. But our focus, because this is just an introductory class, will be on number 2 and number 3. So just sort of get some numerical tools going. And again, if this is stuff that interests you, we go in much more in-depth on this stuff in the CE 528 class. So let's go back to the notes here. So again, this is just sort of different interest group. And here I want to point out that, in travel demand modeling that we learned in chapter 4, which is about if we build a certain facility or given the current conditions, given the existing condition, how many people are expected to use a roadway, a transit facility, whatever it is, a piece of transportation infrastructure. That is what we call travel demand modeling. So travel demand modeling is one part of it. And ultimately, we use that travel demand modeling to estimate benefits and the cost and compare them to costs so that we can actually decide what type of infrastructure to build, whether or not to build certain infrastructure. Okay, so I hope the broader context is clear. And then, and hopefully you're able to see that ultimately we do transportation planning to be able to make better decisions. So decision making is the ultimate goal, not the travel demand modeling. Travel demand modeling is an intermediate step to figure out the benefits of our decisions that we are making. Okay. Role of the MPO. MPO is the Metropolitan Planning Organization. Basically, for this area, it is the San Luis Obispo Council of Government in our region. They make a lot of decisions around where to allocate funding. In the example problem that you saw in the textbook, it's the Mythica County Planning Commission that they were talking about. So that's an MPO. Excuse me. So these MPOs are sort of regional agencies that make decisions at the regional level. So they look at corridors that connect one city in the region to the other, and then they also sort of help out with connections of that region to other regions of the state and the country, right? So they look at that part of infrastructure as well. So they can make a little bit more broader decision making. So what is their role in the transportation planning process? They establish a setting, they determine what's going to be the context of the problem. They are the one that evaluate alternatives. And this is what I've underlined because that's what we're going to focus on. Maintain a long-range transportation plan, a transportation improvement plan that's for the short and medium term. And then it's very important now because the federal government, through their grant funding abilities, so basically they attach the strings to the funding that the MPOs get. They want the public to be involved in the decision-making process. So that's also the role of the MPO, is that before they sort of dole out any funding, before they do anything, they better involve the public because that might be the requirement for the funding that they're getting. But I've highlighted here the evaluation of alternative because that's our focus in this chapter. That's why I've underlined it. So what is engineering economics? What is the role of engineering economics in all this? It helps us rank and rate specific project by looking at economic and financial side of engineering decisions. Obviously, there are other engineering economics topics like inflation, taxation, which are not sort of part of this class, again, because this is just an introductory class. If private benefits are more than private costs, then we know the private sector will come in and fund the project, right? So that's why you don't see sort of government opening grocery stores, for example, right? In most places, grocery stores can make a profit. You don't see government sort of looking at a grocery store or looking at opening and operating grocery store or restaurants, for example, right? Because private benefits can be higher than the private costs. So So somebody from the private sector can come in and make the money. If public benefits are greater than public costs, then one can justify the project, and then pay for it using public costs, right? So that's the scenario that we are dealing with. But if you're thinking about, so in some cases, what happens is that the public benefits are higher than the private costs. So sometimes the government has to incentivize the private sector to provide that. But that's not the scenario we're dealing with in this chapter. In this chapter, we are primarily interested in looking at public benefits and looking at the public costs and seeing public agency costs and public agency benefits and see if we can justify projects based on those behalf. And that's why I've underlined it, is that, we assume that it's the same agency that bearing the cost, and then we estimate the benefits and use those benefits to get the benefit cost ratio. If it's higher than 1, then we look at, which of these projects have the highest benefit cost ratios, for example, right? So we look at different benefits and we look at different costs, and we add up the benefits, we add up the costs, and figure out which is the most viable alternative. So here is sort of the most critical aspect of this. The most critical aspect of this is the time-oriented value of money. Because the project, the transportation infrastructure that we typically build, it's not for 1 year. It's not for 6 months. It's for many years to come. Like, let's say if you build a bridge, we expect that bridge to last 30, 40, 50 years, right? If we buy a piece of equipment, typically, for example, if Caltrans in Lake Tahoe area, for example, if a regional agency or Caltrans buys a snow removal equipment, they don't just buy it for one snow season. They expect it to last multiple seasons. So you're basically making long-term investments. And if you're making long-term investments, you have to be able to look at money from a long-term point of view. And here I'm not talking about inflation, right? So because inflation will typically affect all of these alternatives in the same way. The value of money that gets eroded over time, right? So because what $100 used to buy 10 years ago, they don't buy as much stuff today. That's your inflation. But I'm not talking about inflation, because remember, our goal is to compare alternatives. And when you're comparing alternatives, the dollar value erosion, the erosion of value of a dollar due to inflation, that typically would affect each of these alternatives the same way. So that doesn't really help us in comparing alternatives. What we are interested in mostly here is that if you use the money, then you lose the opportunity to put that money to use in other projects or other alternatives, or even just sort of setting it into the bank and earn whatever you're currently earning, let's say 4% or 5% interest, right? So if you use the money on any project, the opportunity to earn interest on that money is gone. So that's what we call the opportunity cost. So that's why use of money costs more money. Project costs or benefits that occur 5 years from now are worth less in terms of today's dollar. Okay. Again, as I said before, this is not about inflation, but this is about cost of opportunity of using that money for other purposes. So that's a very important distinction to make here. So, but the end result is that, if somebody, so think about it this way. If somebody says, I'll give you $100 today and $100 2 years from now, what would you do? Which alternative would you pick? I would pick $100 today, because if I had $100 today, I can actually make more money for the 2 years period that I have. So instead of having $100 today, let's say if I earn 5% interest, I will have close to $110 in 2 years, right? So that's why the dollars that are available today are worth more, and dollars that are available in the future, like let's say 2 years or 5 years down the line, are not worth as much in terms of today's dollars, okay? Because if you had the money today, you can earn interest on it. And that gives rise to this concept of net present value. How do we estimate the net present value of a dollar? So the net present worth of a project is determined based on present value of benefits minus present value of cost. Okay, and present value basically transforms all the benefits of a project and all the costs associated with the project into today's dollars. Okay, so here's the example here. Okay, so I want to just kind of write down this thing here. So here, what you have is C0, and I'm not using subscript, but this is the C0 I'm referring to here. What is this C0? Okay, C0 is the present value of the cost so anytime you have a project, there's going to be some initial investment involved in that project, right? So just sort of buying the equipment, like, whatever down payment you might be making for that, or, just something that you have to allocate right away. Okay, so that sort of cost of building the infrastructure that has to be allocated at the beginning of the project life cycle. And then the C1 and C2 and Cn, and n is the number of years here. So if you look at the n is the number of year. So this is the life cycle, lifespan of the project in number of years. Okay, so that's your n. So at the first year, the cost of, so C1 is sort of the cost that you're going to have to bear after year one to maintain and operate the project, or the piece of equipment or a piece of infrastructure. Maybe if this is a bridge, maybe cost of sort of examining the bridge, repairing the bridge, all of that. At the end of year two, the cost will be C2. And this is the end of year two. And then C3 in the year three, C4, and then at the nth year, it's going to be Cn. Okay. And then and I'm going to talk about this D and stuff in a minute. And then for the benefits also, so when you build the project, there's not going to be any benefit at the right away. You're not going to get any benefit until you build the project. But maybe after the project is built, you're going to have a benefit of B1 at the end of year one, B2 year two, B3 in year three, and Bn in year n. So C's represent essentially the costs, and these are the benefits. Okay, so I'm trying to use these, but as I told you before, the benefits and the costs that happen not right away, but 1 year from now, or 2 years from now, or 3 years from now, are less in value, have smaller value in today's dollars. And because we're trying to establish a present value, because we're trying to establish this present value, PV, okay, I need to discount all of these future investments. I need to discount all of these future investments, which is C1, C2, because they all happen in the future, Cn, and same thing with B1, B2, and Bn. I need to discount all of them to today's dollars, because that's my goal, is to get the present value. Because my goal is to get the present value, I need to discount all the things that happen in the future into today's dollars. And how do I do that? I do that using a parameter that's called D, which is called the discount rate. So discount rate stands for, why do we call it the discount rate? It's the rate at which, it's the interest rate or the rate at which future dollars are discounted. Okay, future dollars, because again, future dollars are not as much worth as much as today's dollars. I need to discount that. Okay, and typically that rate would be, let's just say 5%, right? So example value of D would be 5%. So let's think about some numbers here. And I want to figure out what is the present value. I want to figure out what is the present value of $100. Let's say C1. Let's say C1. So this is your cost at the end of year one. Our cost in the year one is $100. So if I want to find the present value, okay, and it's the 5% interest that I could have earned. So you're trying to figure out how many dollars you need today so that 1 year from now you have $100. So let's say that value is X, okay? So let's say X is the value, is the amount you need today to get $100 in 1 year. Okay, so if X is that amount, how do you get that? So let's say if you have X dollars today, and then you can earn 5% interest. So at the end of the year one, you'll have 1 plus 0.05 because the interest rate is 5%. So if you have X dollars today, and you can earn 5% interest on it, so in 1 year from now, you'll have X times $1.05. And you're trying to figure out what is the amount you need today to get $100 in the year. So you equate that to 100. So that means basically if you want to estimate X equal to, it'll be 100 divided by 1 plus 0.05. So I hope you can see that what I'm showing you here so this value, I hope you can see that this value, X equal to 100 divided by 1.05, basically gives rise to this term right here, C1 over 1 plus D. Now, if you want to change this example, right, if you want to change this, let's say X equal to amount you need today to get $100 in 2 years. So if I want to sort of edit this to, so not in 1 year, but in 2 years. So if I want to get $100 in 2 years, it will be X times 1 plus 0.05. In 2 years, I'll have basically, because I can earn another 5% interest on the same money. Right? So I'll have this value. So in 2 years, if I want to just sort of change this to 2 years, that should be equal to 100. So if X is the amount you need, so let's call it Y amount. So if I want to get Y is the amount I need in today to be $100 in 2 years, I can estimate Y as 100 divided by 1 plus 0.05 whole square, right? So I hope you can see. So if I stamp it, so you can see that this formula right here, so if I look at this formula, so I look at this formula right here, that's basically my 2-year formula. 100 C2, you know, if I try to find the present value of the cost, if I have $100 in 2 years from now, $100 divided by 1.01 plus D whole squared gives me the present value of these costs. And then you can go on and on for nth year, you get this formula. And then once you've converted everything to present value, you can add them up to get the present value of cost. And remember, I'm not doing any adjustment to C0 because that's the present value of initial investment. That's the investment I need to make right away. So there's no adjustment that's needed. It's only for the future dollars that I need to sort of discount to the present value. And then you could see that this is because 1 plus 0.05 is more than 1. The value of the future dollars is always lower in terms of today's dollar. So it's 100 divided by 1.05, 100 divided by 1.05 whole squared. So D is what we call the discount rate, or 5%. And you can do the same thing with benefits. And there is no benefits right away because you haven't built the project. The benefits start accruing only after the project is built. So you get the B1 over 1 plus D, B2 over 1 plus D whole squared, and Bn over 1 plus D raised to power n. And if you want to get the net present worth, it's basically just benefit minus the cost. So benefit minus the cost. So you basically take this equation and subtract this equation from it, and you're going to get this equation right here. Now, next thing I want to discuss is that what is P given A, D, N, and A given P, D, and N. So these are sort of the special cases where annual costs and benefits are exactly the same. So for example, every year you have a certain cost, and every year you get a certain benefit. So basically, instead of these values being C1, C2, C3, in this case, C1 is equal to C2 is equal to Cn, and then also B1 is equal to B2 is equal to B3 is equal to Bn. So all of these values are equal. If those are equal, that's what gives rise to uniform annual amount A into present worth P. So if you want to, and that's basically just C1 is equal to C2 is equal to Cn, and then that becomes sort of a geometric series, and summation of geometric series have a formula, and then this is the formula you get. So if you have a present value of cost where CIs are all the same times, and you could basically come up with a factor that you multiply by that, your annual cost, and you could get, so it's 1 plus d raised to power n minus 1 divided by d times 1 plus d raised to power n. So that gives you your present value given the uniform annual cost. And in this case, uniform annual cost A's are just nothing but CI. And you multiply this factor. And what's this factor? This is the factor. Okay, so it's this depends on the discount rate, depends on the the life cycle of the project N. So you can convert, let's say, if these values were all 1,000 every year, you can convert these 1,000 into the present value. Okay, so let's do a quick example of this. So let's do a quick example. Let's say D is equal to 5% and N is equal to 10 years. Estimate or calculate P calculate P given A factor. So P given A comma Dn. So I can put that. D is 5% and then 10 is the year. So remember, the factor itself doesn't depend on the P or the A. The factor just has the formula. So if you look at carefully here, the formula for factor is just depending upon just this, right? It just, you multiply that with the annual value. So let's see how we calculate it. I'm going to go ahead and calculate. So it's going to be 1 plus D is always written in terms of fractions, so 0.05. Okay, raised to power 10. And then once you calculate that, you subtract 1 from it. And then you divide this whole thing, whatever this turns out to be, this whole thing is divided by 0.05 times 1.05 raised to power 10. So this is sort of what becomes my factor. And then I can use a calculator to calculate it. And I'm going to just quickly go ahead and do the estimation here. So if I calculate this factor, if I apply this formula and try to calculate it, I get 7.72. If I apply this, I get equal to, this is equal to 7.72. So I can convert any uniform series, like be it $1,000, $10,000, $1 million, $200,000, whatever it is. If I multiply 200,000, so if there is a cost or a benefit stream of $200,000 every year, I can convert that stream by multiplying that into 7.72, right? I can convert into the present value. Okay, so it's basically, if you add up 200,000 for 10 years and you want to calculate its present value, it's going to be so 100. So let's just kind of do a simple equation. So $100 for 10 years, $100 every year for 10 years means we'll have $772 of PV. Now, remember, that's not $1,000 of PV, because that's what nominally, if you add up $100 for 10 years, 100 plus 100 plus 100 plus 100 like that, you add up to $1,000. And now, but if you sort of account for that interest rate, you get 772. By the way, if your interest rate were 0%, if there was no interest rate, if you're not making any money on the $100, if you substitute D equal to 0 in this equation, right? This equation doesn't quite work, right? You cannot actually estimate the value. But if the D is 0, then that means that your individual sort of so the present value of each $100 would be 100 over 1 plus D, which is 0. So 100 over 1, 100 over 1 square, 100 over 1 cube. So if for example, in the previous slides, if I go to the last slide, if D equal to 0, it's C1 over 1, C2 over 1 plus 0 squared, Cn over 1. So basically, all these values would be the same. You're just dividing by 1. And in that case, your $100 each for every year for 10 years will have a present value of $1,000. So higher value if you have no interest rates. So again, a corollary of that is that if your interest rates are low, right, the discount value is closer to the present value. So you'll get like a higher number. So you can test that out by sort of playing around with the interest rate and computing that factor. Now, the other thing you could do is if you can invert this factor, you can take the reciprocal of the factor that you just got, 7.72, and you can convert sort of a present value, a certain present value for today's dollar, and you can annualize it. Okay, what's the equivalent uniform annual cost of a certain cost? So sometimes you might need to do that, and we'll discuss the examples of that. But let's say if you have $1,000 of initial investment, and you want to figure out at 5%, discount rate, what's the uniform annual cost? What's the equivalent uniform annual cost? Over 10 years. If you want to do that, that's pretty easy, because what you can do is you can just take the same factor and do the reciprocal of that factor. So basically, instead of multiplying by 7.72, you might multiply by 1 over 7.72, which is the same as dividing by that. So you take the $1,000 and divide that by 7.72, and you will be able to get what the value is for. So if you take so I'm just going to quickly calculate. So if you take $1,000, divide that by 7.72, you get $129.53. So equal to $129.53 for 10 years. So if you take $129.53 for 10 years, that'll add up to $1,000 of cost, uniform cost every year. So 129.53 in year 1, 129.53 in year 2, and on like that for 10 years. You add up the present value of all of those, they will add up to $1,000 at the very beginning. So this is what I mean by these two factors, P given A and A given P. Basically, there are the same factors, but one is just reciprocal of the other. So this is very important, that when you're comparing alternatives, we convert all the costs and all the benefits into today's dollars. So make it a present value. And then, we sort of do the same thing with and then we can, once we have them converted into present values, you can calculate net present worth like we did in the slide here, benefit minus the cost. And you can compare whichever alternative gives you the highest net present worth. We can also do benefit cost ratio, B by C ratio. It's just basically net present value of benefits divided by net present value of costs, or sorry, present value of benefits divided by present value of costs. So this is just, so if I want to write it down, it will be PV of benefits divided by present value of benefits divided by the present value of costs. But again, they have to be present value. You have to convert all the streams of cash flow into today's dollars. Now, one thing is that, which one to choose between net present worth and benefit cost ratio. In this class, for the purpose of this class, I'm going to always tell you what I'm looking for. Okay, so I'm always going to tell you that, and you're just going to give me that value. However, if you're interested in learning more about when do you apply which of these metrics, then we cover that in CE 528, which is the Transportation Economics and Analysis class. Okay. Now, one thing is that sometimes, as I was saying, sometimes you don't want to convert everything to present value. In fact, you want an annualized stream. When do you want that? Okay. When do you want that is that sometimes when we're comparing alternatives, sometimes alternatives have different lifespan. So for example, think of it as a comparing between buying a new car versus buying a used car. If you buy a new car, it'll obviously have higher cost at the beginning, right? You might have to pay more, right? But then it lasts longer. If you buy a used car, there's a good chance that maybe that doesn't last as long as a new car, right? But if you start making decision based on present value, it'll always take you towards the used car. So think about that, right? So let's say the operating costs are the same for the new and used car. And when I say that, I know that's a big assumption, but maybe a reasonable one, given that maybe the used car has more maintenance cost, but maybe not as high of an insurance cost, right? But the new car has maybe little to no maintenance cost, but it'll have, your insurance costs would be higher, and maybe, so let's just assume that their annual costs are the same, what you have to pay to maintain them and get insurance on them and all of that. Let's say both new and used car have the same value of these annual costs. And but the new car costs more money to begin with. So let's say maybe $40,000, and then you can get a used car for $10,000. Now, if you start making those decisions just based on present value, convert everything to today's dollars, that won't be appropriate, right? Because what you're not accounting for is that the new car is going to last probably longer than your old car. So you want to make an apples to apples comparison. To do that, if your projects have different lifespans, if alternative A is going to last 10 years and alternative B is only going to last 5 years, what you want to do is you want to convert not to present value, you want to convert everything into an annualized amount. So that's where that other factor, this other factor, A given P, comes into play. And that's what we try to do. So that's what, so anytime you see, I'm asking you to compare alternatives of different life cycles, then what you try to do is you compare them based on the equivalent uniform annual cost. Okay. So here are two example problems that we're going to work on in this class. And this is example 5.2 and example 5.6 from your textbook. And I'm going to record separate videos for these examples. But I want to quickly talk a little bit about those. So example 5.2, proposed project can be accomplished with two technologies. Version A is accomplished by investing 8 million. So this is your present value. So this part is your, so if you look at this $8 million, this is your present value. So this is your PV. Okay, the 8 million is the PV. Operation and maintenance cost is $60,000 until the project reaches lifeline of 20 years with no salvage values. This is another thing, right? Sometimes when the projects end, you can maybe get the scrap metal out of it and sell it for that scrap metal prices and get some value out of it after its useful life has gone away. Now, if you look at version B here, so second alternative is version B, is investing a much higher amount of $14 million. So the present value for B, so this is your PV value. So this is the PV, $14 million, much lower operation and maintenance, O&M costs. Operation and maintenance is only $100,000 per year. So that's pretty good. You don't have to spend but remember the first one had an operation cost of $860,000. Version B will have a residual salvage value of 3 million at the end of 20 years. So again, so these two have the same life cycle. So this had a life cycle of 20 years, alternative A did. Alternative B had a life cycle of 20 years as well. If the discount rate is 10%, which version should be chosen? So now, because the projects have same life cycle, I could convert everything into present value. Okay. So, and then again, the other thing it's telling you is that how do we collect that? So I'm going to, in the exam, I'm always going to tell you that, hey, give me the value or the estimate of what you're going to pick based on the net present worth of the alternative. And if I want you to get benefit cost ratio, I want you to use benefit cost ratio as well. Okay. So this is an example 5.2, and let's try to figure out how we're going to sort of start approaching this problem. So first of all, because I'm converting everything to present value, question to you is, would I be applying any correction to the present value of investment? So let's look at the alternative A first. It's at an $8 million cost. I'm not going to apply any adjustment to it because this is already present value, so it's already in today's dollars. And my cost of operation and maintenance is $860,000. So $860,000. So what I'm basically coming up with the present value of costs, and there is no benefits associated with that, right? So I just have to make the decision based on which of these alternatives cost less, right? So I'm just going to convert everything into present value. So how do I convert the $860,000 into present value? I use the formula that I had. I'm gonna go ahead and copy that formula. Okay, so I'm gonna go ahead and bring that formula over. So if I have this formula right here, I'm gonna use it. So 8 million plus. So I'm gonna apply that to $860,000. So I'm gonna convert this $860,000 of cost into today. This is annual cost. So I'm gonna convert that annual into present value. So I can get present given annual with this formula. So the CI is $860,000. I'm gonna multiply that by 1 plus, it says discount rate is 10%. So I'm gonna just make it 0.1. And it's a 20-year life cycle. So I'm gonna do raised to power 20 minus 1. Right? And I'm gonna divide this whole thing by I'm adding here. I'm going to divide this whole thing by d times 1 plus d raised to power n. So my next formula is this part. D is 0.1. I'm going to divide that by 0.1 times 1.1 raised to power 1. Right? Does that make sense to everybody? Right? So if you do that and you compute all this, you're going to get the present value of alternative A. And then you could do the same thing for $14 million. So you can do the same thing for $14 million. So in the alternative B, for alternative B, what does that look like? So it's going to start with $14 million. So you're going to start with a bigger hole, but then the cost is only $100,000 per year. And the beauty is you actually don't have to compute this again and again and again. You could use that same factor that you compute for, if the D is the same and the N is the same, you can apply the same factor. So I'm going to say same P given A factor that you computed for alt A, right? So you can multiply that 100,000 with the same P given A factor, and you got this, right? But now you have a salvage value that you haven't accounted for, right? So you have $3 million that you're going to get at the end of 20 years. It's only a one-time thing. So the P given A factor won't work here. So remember, I can't just, so for the $3 million, I cannot apply this factor. Why can't I apply this factor? Because it's not $3 million year after year after year after year. I don't have that. I only have $3 million one time, right? And that's the end of 20 years. So I need to just convert that $3 million at the end of 20 years into today's dollars. And that will subtract from my cost, because remember, so what I'm gonna do is I'm gonna subtract from this cost minus, so it's gonna be 14 million plus 100,000 times the P given a factor minus 30 million converted into today's dollars, the 30M, divided by 1 plus 0.1 raised to power 20, just one time, because it's 20 years down the line. Oh, I'm sorry, not 30 million, but 3 million. $3 million divided by 1.1 raised to power 20, just one time. I'm going to, at 20 years, so it's just basically converting the $3 million into today's dollars. And then whatever these values give me, I should be then able to compare. Okay? So that's great. So I hope you got to give it a try. And this is example 5.2. Don't forget to read up the discussion that's on the, they talk a little bit about how public agencies sometimes have limited budget. So even if alternative B comes out to be lower cost at the end, in terms of doing the analysis and converting, some agencies might decide, $14 million is too much to spend right now. Even though it's the right choice from a present value perspective, we still want to go with only $8 million alternative. So that could still happen. So there could be other consideration, but we're not going to worry about those considerations in the class. But it's just that it's good to read those discussions and be aware of those. So if you go to the example problem in the class, so if you go to this example problem in the class, I'm going to just clear out all the drawings. But if I go to example number 5.2 here, you will see that in this case, present value of cost of B, so the factor came out to be 8.51. So you can see that they use the same factor, and then 1.1 raised to power 20, so divide by that. And then you could see that alternative A came out to be 15 million of net present cost. Alternative B has 14 million. So they don't actually go with the low. You should go with B here, right? So if you had to pick one alternative, I'll pick B. Version B has lower cost, but other factors may enter into the topics of choice of technologies, because public sector budgets are limited. And then time of the next election might be in play. So sometimes they might choose version A to sort of lower the initial cost, right? So there could be other factors at play as well. So we need to be aware of those. But that's something to look at. Now let's think about this other example. And I'm not going to sort of solve this example for you, other than to say that in this example, the big difference is this right here. The big difference is that the life cycle of the three alternatives is 20 years, 30 years, and 15 years. Okay, so if you're picking between X, Y, and Z, and they have different life cycles, you cannot convert everything into present value. You have to convert everything into annualized cost. Okay, using the discount rate of 5%. So they're telling you a discount rate of 5%. And what I will do is, like, I will just come up with a way of annualizing the cost at D equal to 5% and life equal to, so in here, so D will always be 5%, but the N will be 20, N will be 30 here, and N will be 15 for this alternative. And I'll come up with the factor to convert the present value into annual value. Okay, so I'll leave these things untouched. I'm going to leave the annual costs and annual benefits untouched in this example, right? Because those are the values that I'm going to not convert, because I want to convert everything into annualized amount. I will convert this one. I will convert this into today's, they are in today's dollars, and I'll convert into an annualized series. How am I going to do that? I'm going to do that using the reciprocal of this factor, not this factor, but the reciprocal of this factor. So I'm going to sort of divide by this factor to get the annualized stream for this one. Now, the interesting question is, and I'm going to leave that up to you, I'm not going to answer it here. What are you going to do with the salvage value? Salvage value is a one-time value that happens at the end of the life cycle. So for this example, for the alternative X, the project X, at the end of 20 years, you get $30,000 in salvage. For Y, you get $100,000 in salvage at the end of 30 years. For alternative Z, you get $2 million of salvage at the end of 15 years. how do you convert that into an annualized amount? That'll be an interesting question. You might have to do some step-by-step process. So think about that a little bit as well as you are looking at this. Okay. So this is sort of the numerical analysis that I want you to do. And again, numerical analysis is not sufficient all the time. And if you're interested in that discussion, you should take the CE 528 Transportation Economics and Analysis class. And here, one more thing I want to talk a little bit about, the last slide, is that ranking transportation alternatives sometimes becomes a multi-attribute effectiveness analysis process. So we look at sort of different measures of effectiveness, and your textbook does a good job of it by giving you sort of an apartment choice example. So I want to take a look at that just real quick here. So how do you rank a transportation alternative? So what attributes are you? So this is the example I wanted to come up with here. And there are some think about it type questions here. What attributes are you likely to consider in choosing a place to live? Once you've made an initial list, try to rank your attributes from most important to the least important, right? So sometimes you have to sort of think about the rent will be a factor, how far you are from campus would be a factor. So that becomes sort of a multi-criteria problem. And again, in transportation, there are several of those because there might be costs involved, there might be benefits involved, there might be other things that go on. So we have to sort of account for that. And this is why I want you to read through this apartment choice example. And again, there's no numerical problems that I'm going to ask you to solve. I just want you to go through that reading exercise and figure out, the rent per month, how much weight you want to assign to that. And then based on that, you come up with a measure of effectiveness and then distance of campus. So the rent for Bloomfield apartment is higher and East Library is lower, but East Library is farther from the campus. And then based on that, how do you make a decision? So that becomes like, how much weight you want to provide. And then they give you some examples of the real world infrastructure problem as well, which I'm not going to get into. And we can look those over later on. But my goal would be for you to read through this example 5.4. All right. So with that, I'm going to stop here. And once you've done all of this, you can go to your Canvas page. So let's see if I'm at the right Canvas page here. Nope. So this is the other class. If I go to my courses, I go to 321. I'm going to post this recording here. But now for the example problems for the week, for this week, you can work on 5.2, 5.6, and 5.7 as well. After you've watched this video and you've gone through the lecture notes and you've done the reading, you could also solve example 5.2, 5.6, and 5.7. Thank you so much.